Welcome, everyone, to today's episode, where we're diving deep into the enigmatic world of black holes. We'll explore everything from their formation to the mind-bending effects they have on space-time. I'm thrilled to have our expert and inquisitive learner with us today to unravel these cosmic mysteries.
I'm excited to be here. Black holes have always fascinated me, but I'm hoping we can break down some of the more complex concepts. I've got a ton of questions about how these things actually work and what we're still trying to figure out.
It's a pleasure to join you both. Black holes are a cornerstone of modern astrophysics, and there's so much to discuss, from their mind-bending physics to the latest discoveries. I look forward to sharing some insights and hopefully sparking some new curiosities.
All right, let's jump right in. What exactly is a black hole? I mean, we hear the term thrown around, but what are we really talking about?
Yeah, is it just a big cosmic vacuum cleaner? Like, does it just suck up everything in sight?
That's a common misconception. A black hole is essentially a region in space-time where gravity is so strong that nothing, not even light, can escape. It's a concentration of mass in an incredibly small volume.
So it's not necessarily about sucking things in, but about the intense gravitational pull, right?
Okay, that makes more sense. But how did we even think of such a crazy thing? Did someone just wake up one day and say, hey, what if gravity was, really strong?
The concept actually dates back to the 18th century. People like Jean Michel and Pierre-Simon Laplace theorized about dark stars, objects so massive that their escape velocity would exceed the speed of light. But it was Einstein's general theory of relativity that provided the theoretical framework we needed.
Ah, Einstein. Always bending our minds, and space-time, apparently. So, relativity laid the groundwork. Then what?
Yeah, take us to the juicy details. I want names and dates.
Well, in 1916, Carl Schwarzschild found the first exact solution to Einstein's field equations, describing the gravitational field around a non-rotating spherically symmetric mass. This introduced the concept of the Schwarzschild radius, which is crucial for understanding black holes.
The Schwarzschild radius sounds important. So, what are the key components of a black hole? What are the essential ingredients?
Yeah, what are the must-haves? Event horizon, singularity. These sound like sci-fi movie titles.
Precisely. The event horizon is the point of no return, the boundary beyond which nothing can escape. Then, at the very center, there's the singularity, a point of infinite density where our current laws of physics break down. And, as we mentioned, the Schwarzschild radius defines the size of the event horizon for a non-rotating black hole.
Okay, so event horizon, can't escape. Singularity, all the mass squished into a single point. And the Schwarzschild radius tells us how big the no-escape zone is. Is that a good way to think about it?
So if I cross the event horizon, I'm toast? No turning back?
In theory, yes. Once you cross the event horizon, you're destined to be drawn towards the singularity. But the effects would be dramatic, to say the least.
All right, now that we've got a handle on the anatomy of a black hole, let's talk about the different types out there. It's not just one size fits all, is it?
Oh, goody. Black hole taxonomy. I'm picturing, little black hole field guides. Ah, yes. A Stellaris divoris. Quite common in this sector.
Indeed, black holes are categorized primarily by their mass, which also gives us clues about their formation.
So let's start with the most common ones. Stellar mass black holes. How do these guys come to be?
Stellar mass. So regular star-sized?
They form from the gravitational collapse of massive stars much bigger than our sun, at the end of their lives. When these stars run out of fuel, their cores collapse, often triggering a supernova explosion. If the remaining core is massive enough, it collapses into a black hole.
Supernova explosion. So a star goes out with a bang and leaves behind a black hole as a souvenir. Any famous examples of stellar mass black holes?
Ooh, name drops. I love it.
Cygnus X1 was the first widely accepted black hole candidate. It's part of a binary system, pulling material from a companion star.
Cygnus X1, a classic. Okay, so that's stellar mass. What about the big boys? I'm talking supermassive.
Supermassive. Do they eat a lot of stars to get that big?
Well, they're found at the centers of nearly all large galaxies, including our own Milky Way. Sagittarius A NAR is the supermassive black hole at the center of our galaxy, with a mass of about 4 million suns.
4 million suns. That's a lot. And it just sits there in the middle of our galaxy?
Doing what exactly? Ruling the galaxy with an iron, or rather gravitational, fist?
It influences the orbits of stars nearby, and it occasionally flares up as it accretes matter. Also, the Event Horizon Telescope gave us the first ever image of a black hole, and that was M87's supermassive black hole, which is even bigger, about 6.5 billion solar masses.
Wow. Okay, stellar mass, supermassive. Are there any other types of black holes we should know about?
Yeah, what about the black holes that are, tech just right? Not too big, not too small?
That would be the intermediate mass black holes, or IMBHs. They're harder to find, but we're gathering more evidence for them. And finally, there are primordial black holes, which are hypothetical objects that might have formed in the very early universe.
Primordial black holes. Now that sounds like something out of science fiction.
Ooh, could they be the dark matter everyone is always talking about?
It's a possibility. The existence of primordial black holes is still purely theoretical. They are considered potential candidates for dark matter, but we have no direct observational evidence yet.
Okay, so we've talked about what black holes torosize and the different torosizes they come in. Now, how do these cosmic vacuum cleaners actually torosize? Form NOS. Let's start with stellar mass black holes. What's the recipe?
All right, so we're going from black hole anatomy to black hole embryology, huh? I'm picturing a cosmic stork delivering baby black holes.
The primary mechanism for stellar mass black hole formation is stellar collapse. It's a dramatic end from massive stars.
Stellar collapse it is? Walk us through it.
So a big star gets old and tired, runs out of gas, then what? Does it just sort of deflate?
Not quite. When a massive star exhausts its nuclear fuel, the core collapses under its own gravity. This triggers a supernova explosion.
Supernova. We love a good explosion. And then, poof, black hole?
Wait, so the supernova is like the black hole's dramatic birth announcement?
Essentially, yes. If the remaining core after the supernova is massive enough, above a certain limit, gravity wins and it collapses into a black hole.
Got it. So that covers the stellar mass ones. What about the supermassive black holes lurking at the centers of galaxies? Do they form the same way?
Yeah, I can't imagine a single star going supernova and leaving behind something 4 million times the mass of the sun.
The formation of supermassive black holes is more complex and still an area of active research. Accretion and mergers play a key role.
Accretion and mergers? Sounds like they're not born, but assembled.
So like cosmic Legos? They just keep adding pieces until they're giant?
Black holes can grow by accreting gas, dust, and even other stars. They can also merge with other black holes, gradually increasing their mass over time.
So they're like galactic Pac-Men, constantly munching on everything around them. Okay, stellar collapse, accretion, mergers, got it. Now the big question, how do we even find these things if they don't emit light?
If light can't escape, how do we see them? Is it like some sort of cosmic magic trick?
Detecting black holes requires observing their effects on their surroundings. We primarily use gravitational effects, X-ray emissions, and, of course, gravitational waves.
All right, let's break that down. Gravitational effects. Like what exactly?
Is this like when you can tell someone's secretly a Jedi because they can, like lift rocks with their mind?
We can observe the orbits of stars near a black hole. If a star is orbiting an unseen, massive object at very high speeds, that's a strong indication of a black hole's presence. Gravitational lensing is another tool.
Okay, so watching how stars move around them. Got it. What about X-ray emissions?
X-rays? So black holes give off radiation when they're angry?
When matter falls into a black hole, it forms an accretion disk that heats up to millions of degrees, emitting intense X-rays. These X-rays can be detected by telescopes.
So it's more like a cosmic burp than anger. And finally, gravitational waves. Those are the ripples in space-time, right?
Gravitational waves. Can we surf on them?
The merger of two black holes creates significant gravitational waves that can be detected by observatories like LIGO and Virgo. This has opened a new window into black hole astronomy.
Absolutely. So to recap, we find black holes by looking at how they affect the things around them, the movement of stars, the X-rays they emit, and the gravitational waves they produce. It's like being a cosmic detective.
Elementary, my dear Watson. The black hole is always the culprit.
Indeed. Each method offers a unique perspective on these fascinating objects, complementing each other to build a more complete picture.
All right, folks. Buckle up, because now we're diving into how black holes warp the very fabric of reality. I'm talking about space-time.
Space-time, huh? So like, if I get close enough to a black hole, will I see the universe doing the twist?
Indeed. According to Einstein's general relativity, massive objects like black holes curve spacetime. This curvature is what we experience as gravity.
Exactly. And that curvature has some seriously mind-bending effects. Like, let's talk about time. What happens to time near a black hole?
Ooh, time travel? Do black holes come with a return option?
Not quite. However, time dilation occurs near a black hole. Time passes more slowly for an observer close to the black hole compared to someone far away.
Time dilation. It's like the ultimate cosmic slowdown. Imagine watching a clock fall into a black hole. From a safe distance, of course.
So from my perspective, the clock would look like it's moving slower and slower until it just freezes?
Precisely. Theoretically, at the event horizon, time would appear to stop completely for the infalling object from an outside observer's viewpoint.
Whoa. Okay, time is relative, got it. But what about space? Does a black hole mess with space too?
I'm guessing it's not just a gentle hug, more like a cosmic wedgie?
The extreme gravitational gradient near a black hole generates very strong tidal forces.
Tidal forces, which brings us to spaghettification. Can you paint us a picture?
Spaghettification? Is that like becoming cosmic pasta?
In essence, yes. If an object gets too close, the difference in gravitational pull between its near and far ends becomes so extreme that it's stretched out, like spaghetti.
So you'd be stretched into a long, thin noodle before you even reached the event horizon? That's intense.
Note to self, pack extra long noodles for black hole expeditions.
It's worth noting that for supermassive black holes, the tidal forces at the event horizon are weaker. So, theoretically, one could cross the event horizon without immediate spaghettification.
But only to meet your doom later. So to recap, black holes warp spacetime, causing time dilation and spaghettification. They are truly the universe's ultimate special effects artists.
So black holes, bad for your health but great for bending reality. Got it.
Indeed. These effects highlight the extreme nature of black holes and their profound influence on spacetime.
Alright, so we've journeyed to the event horizon and back. But even with all this mind-blowing science, some mysteries still cling to these cosmic enigmas. Let's dive into some unresolved questions, shall we?
Mysteries, huh? Like, are black holes secretly portals to other dimensions? Please say yes.
While the portal idea remains in the realm of science fiction, there are indeed profound theoretical challenges we're still grappling with.
Exactly. First up, the information paradox. What happens to all the stuff that falls into a black hole?
You mean like, does my old pizza end up in some cosmic landfill?
Quantum mechanics dictates that information cannot be destroyed, but this principle seems to be violated when something enters a black hole, creating a paradox.
It's a head-scratcher. Does the information get stored somehow on the surface, or is it lost forever? And then there's Hawking radiation. Professor, can you illuminate us?
Hawking radiation? Sounds like a sci-fi sunscreen.
Hawking theorized that black holes aren't truly black, but emit a faint radiation due to quantum effects near the event horizon. This radiation could eventually lead to the black hole's evaporation.
So black holes are slowly fizzling out like a cosmic sparkler? That's wild! But detecting this radiation is proving to be a Herculean task, right?
So no one's actually seen Hawking radiation? Are we sure it's even real?
The predicted temperature of Hawking radiation is incredibly low for astrophysical black holes, making direct detection extremely difficult with current technology. However, its theoretical implications are profound.
Absolutely. Which leads us to current research. What are scientists focusing on now when it comes to black holes?
Besides finding out where my socks go when they disappear in the dryer?
Currently, key areas include understanding how supermassive black holes formed so quickly in the early universe, confirming the existence and properties of intermediate mass black holes, and ultimately, developing a theory of quantum gravity that can reconcile general relativity with quantum mechanics.
So SMBH formation, IMBH conformation, and the ever-elusive quantum gravity. It sounds like there's a whole universe of discoveries still waiting to happen. Any final thoughts, Professor?
Yeah, is there any chance we can harness black holes for, like, unlimited energy?
While harnessing black hole energy is currently beyond our technological capabilities, the ongoing research promises to reveal deeper truths about the universe and the fundamental laws that govern it. The journey of discovery continues.